these times. Okay, let's start. Can you hear me?
Yes,
Hello?
sir. Yes, sir. Yes.
Can you people hear me?
Yes, sir.
Hello, can you hear me?
Yes, sir.
Hello? Okay, so you can hear me, fine. Very good. Let's start our lecture today. So, as in every lecture, we have fixed a prime number P, and QP is the field of periodic numbers. And we had defined these quadratic characters of QP star. These are the basic quadratic characters. What are they? For P different from 2, there are two basic characters, nu P and lambda P. So the nu P was the unramified quadratic character. It was defined in terms of the valuation, periodic valuation VP on the field QP. And this lambda P was defined basically in terms of the Legendre symbol. Now for P equal to 2, instead of having just two basic characters, we have three basic characters. There's nu 2, which is analogous to nu P, and that's the unramified quadratic character of Q2 star. Then there are these two characters, lambda 4 and lambda 8 plus, which come from the two characters of Z mod 4, the character of the quadratic character lambda 4 of Z mod 4, and the quadratic character lambda 8 plus of Z mod 8Z star. You first go modulo Z star here, and then that's a group of order 2, so it's isomorphic to Z star. Here lambda 4 is also an isomorphism, and these two, this and this, they give rise to quadratic characters of Q2 star. You see these nu P and nu 2, the unramified quadratic characters are defined independently of any choices. But the character lambda P and the characters lambda 4 and lambda 8 plus depend upon the choice of what is called a uniformizer. So you can take the prime number P itself to be the uniformizer, and that everything is fine, right? But somebody could choose a different uniformizer, like minus P, for example, and nothing will go wrong if you choose minus P either. But what you call lambda P will be a different quadratic character, maybe a different quadratic character from what you call lambda P if you had chosen P as the uniformizer. Okay, so here is the basic definition for today's talk. It's called the quadratic Hilbert symbol. Now, the approach I have chosen today is to do everything explicitly. So we will write down some formulae, and you might wonder, where do these expressions come from? The answer will come later. So towards the end, at least, I will explain why you define this quadratic Hilbert symbol the way I'm going to do it today. Okay? So it's a symbol, it's a map from QP star times QP star to Z star plus minus 1. Z star is just plus minus 1, right? This group. So for A and B in QP star, you first define this gamma AB by this expression. It's minus 1, and these are the minus 1 to the power, the product of the valuations, and then A to the power the valuation of B, and B to the power the minus the valuation of A. So this gamma is actually an element of ZP star. It's a unit because minus 1 to any power, that's a unit, and A to some power, the valuation of B, and B to the power minus the valuation of A, these two things the valuations will just add up to 0. So it will be a unit. Now, if it's a unit, then I can apply lambda P to it. And I could have applied lambda P even if it were not a unit, but then a choice of uniformizer would have been involved. But lambda p for a unit, it's independent of the choice of a uniformizer, right? It's just a map zp star to fp star, and then you have this lambda p from fp star to z star, and the whole thing is being called lambda p as well. So AB, the Hilbert symbol ABP for P different from 2 is defined as lambda P of this gamma AB here, right? Okay, that's a definition. So it's just a matter of finding out whether this gamma AB is a square or not a square. That's what this lambda P keeps track of, right? For P equal to 2, the definition is very different. The first difference is that you have these 3 quadratic characters. Now, first you have to convert them from this multiplicative notation to this additive notation. See, Z star is a group of order 2, so is Z mod 2Z, and they're canonically isomorphic. You send an element A to minus 1 to the power A, and you send an element S to what can be called log minus 1 of S. Doesn't matter. I mean, this is just the name of the isomorphism between these two groups. That's one isomorphism, and that's the reciprocal isomorphism between these two groups of order 2. One written multiplicatively, the other written additively. That's the only difference between these two groups. But that makes a difference because Z mod 2Z can also be thought of as a field. So not only can you add things, not only is it a group, it's also a ring. You can multiply things. And that's why we are converting these 3 quadratic characters from having values in a group to having values in a field here. So, and the new names are going to be these 3 names: V2 bar, epsilon 4, epsilon 8 plus. So here is the explicit definition. This V2 bar is defined so that nu2 is just minus 1 to the power V2 bar of x for every x. And lambda 4 of x is minus 1 to the power epsilon 4 of x. Lambda 8 plus of x is minus 1 to the epsilon 8 plus of x. So that's it. I mean, this is not complicated. It's just, you just have to remember the notation, and the notation has been chosen to be as canonical as possible. This 4, for example, reminds you that there was this 4 here, and the 8 reminds you of the 8 here, etc. Right? So the notation has been chosen as well as I could. And here is how to define. So this is a small, before I define it, here is a small exercise for you people, which is to check that if I take an x in Q2 star and I denote by x bar its image modulo squares, then in that space, x bar is going to be equal to minus 3 to the power v2 bar of x, minus 1 to the power epsilon 4 of x, and 2 to the power epsilon 8 plus of x. So this is a small checking. Anyway, here is the Hilbert symbol which we wanted to define. We have done it for p odd, and this is for p equal to 2. AB of AB2, so A and B are of course in Q2 star, is minus 1 to the power this expression. Well, so another way of writing it is that it's minus 1 to the power this here times epsilon lambda 8 plus of this gamma AB. Gamma AB was this element which we had defined here. This was gamma AB. Okay. So that is the definition of, oh, okay, what is UA and what are UA and UB? So these are the units defined by this. When you write, I mean, maybe I should have written A is 2 to the power V2 of A times UA, and B is 2 to the power V. P is 2 here. V2 of B, UB. So UA and UB are in Z2 star. Okay. So this is the definition. Actually, it's the solution to some problem which we will come to next. And this is the problem. The problem is, suppose you have A and B in QP star. When do there exist X and Y in QP star such that this equation holds? So this is what we will prove at the end of the lecture today, that there are solutions XY to this equation if and only if this AB, what happened? If and only if, oh goodness, right, if AB, P is equal to 1. So if and only if the Hilbert symbol is 1, does this equation have a solution, X comma Y, right? Okay, so here is a small exercise which you people should enjoy doing. You know, we want to define a Hilbert symbol for AB in R star. We have done it for QP star for every prime P. Let's define it for A and B in R star. Of course, it should have values in Z star, which is plus minus 1. So the Hilbert symbol of AB is going to be denoted AB. For AB in R, it's going to be denoted AB infinity. So, and it's going to have values in Z star. And it should be equal to 1 if and only if there exists xy in R such that ax squared plus by squared is equal to 1. See, that's the condition, that's the theorem that we are going to prove for the Hilbert symbol over QP. This is the result which we will prove at the end of the lecture, that AB is equal to 1 if and only if this equation ax squared plus by squared equals 1 has a solution xy in QP. So similarly, for replacing QP by R, for AB in R star, we want to define AB infinity in Z star so that AB infinity is equal to 1 if and only if there are xy in R such that ax squared plus by squared is equal to 1. Okay, so this here is a fact which is a global result. Global means it's about Q and not about QP or R. So this is called the Hasse-Minkowski theorem. It says that if I have two rational numbers A and B, which are non-zero, and I'm interested in solving the equation ax squared plus by squared equals 1 in Q. So I want to find x and y in Q which satisfy this equation. The result of Hasse and Minkowski says that this happens if and only if the Hilbert symbol is equal to 1 for every prime P and for P equal to infinity. In other words, this equation has a solution, in Q if and only if it has a solution in QP for every prime P and in Q infinity, which is the real numbers. So that's what this theorem of Hasse-Minkowski says. We are not going to prove this. But that's one of the basic places where the Hilbert symbol is used, right? But it's a purely local thing. I mean, these A and B don't have to be in Q star. For the Hilbert symbol is 1. If they are in QP star, here A and B are in QP star, then the Hilbert symbol is 1 if and only if this equation has solutions xy in QP, right? Okay, so here are some of the basic properties of the Hilbert symbol. We have defined the Hilbert symbol by an explicit formula. We have defined it by an explicit formula, and we have said that the basic reason why it's interesting and useful is that it tells you when this equation is solvable. But before we prove that result, we have to establish some elementary properties of the Hilbert symbol. So the first property is symmetry. And the second property is multiplicativity. You have BC here and B here, C here. So that's multiplicativity. The third property is this one. A minus A, P is always equal to 1 for every A in QP star, of course. And here is the most interesting property, which is sometimes called by the name of Steinberg. So it says that A1 minus AP is equal to 1 whenever A is different from 1, of course. If A is 1, then this becomes 0, and that doesn't make sense. The Hilbert symbol is defined for A, B in QP star, right? Then you have this Hilbert symbol ABP, which is in Z star, which is plus minus 1. So let's prove these things. For symmetry, it's obvious for P equal to 2. You just look at the formula and see that its definition is symmetric. So it's obvious. For P different from 2, for P odd, let's see what happens when we change A and B in gamma. So it was used, the Hilbert symbol was defined using this gamma AB, right? So if I change A and B, gamma BA turns out to be the inverse of gamma AB. And of course, lambda P of X inverse is equal to lambda P of X for any X in ZP star. Because X is a square if and only if X inverse is a square, right? That's obvious. Okay. So let's come to this multiplicativity here. Again, maybe this is obvious for P equal to 2, or maybe it follows from the fact that, so basically these things follow from the fact that these things are homomorphisms, right? So VP, for example, is a homomorphism from QP star to Z, right? It sends VP of XY is VP of X plus VP of Y. Okay, maybe that's what I've written. So similarly, the other quadratic characters, they are actually homomorphisms, and that is why this multiplicativity holds. So if you don't believe me, you can do this explicit calculation. I mean, gamma, you have to compute gamma of A comma BC. So by definition, it's going to be this. But then VP is multiplicative here, here. So, you get this expression and etc., etc. I mean, this is something that you can check. So the first corollary is that it's multiplicative in the first variable as well, of course, because it's symmetric and multiplicative in the second variable. So that is clear now. And the other thing is that the value ABP depends only on the residue classes of A and B. Residue is not the right word, perhaps. On the equivalence class of A and B, modulo QP star squares. So, and so basically this Hilbert symbol is a symmetric bimultiplicative map from QP star modulo squares times QP star modulo squares into Z star. So I've made this thing more explicit here, that if I have A and B squared, then AB squared P is always equal to 1 for any AB in QP star. That's because of multiplicativity, right? AB squared P is going to be equal to AB P times AB P, which is always equal to 1. You know, the product of any two elements in Z star is 1. The product of the square of any element in Z star is 1, not the product of any two. The square of any element in Z star is 1. Okay. So then we come to A minus A, P equals 1. So again, this is not very difficult to check, because, for example, for P different from 2, gamma A minus A is actually equal to 1. So obviously it's gamma P of 1 is of course 1, right? Okay. Yeah. So we now come to some explicit computation of this Hilbert symbol. So first, let's look at odd primes P. And if I have two units A and B, then AB of P is always equal to 1. So they have to be units, both of them, right? And AP P, this Hilbert symbol, is equal to lambda P of A. And what is the answer? Oh, I mean, how do you prove this? It's just a matter of computation, because I've given you an explicit formula, right? So compute using the explicit definition of this Hilbert symbol. Similarly, for P equal to 2, this was the case, P different from 2. And for P equal to 2, you have, even if A and B are units, this doesn't always equal 1, as in this case. It equals this here. What happened? Why is there something? Yeah, so the screen has disappeared. Let me see. Can you hear me?
Yeah, you're.
Hello.
Yes, we can hear you. Yeah. Did you close your screen that you were sharing?
Okay, so why is it not? Okay, I'm sorry. Can you hear me now?
Yes. Yes.
Okay, so let's continue. So for P equal to 2, No, it's not. Well, it's working very slowly, perhaps. Yeah, it's working. Okay. So for p equal to 2, you have these formulae. A and B are units. Then AB2 is minus 1 to the power epsilon 4 of A, epsilon 4 of B. Right? So what is epsilon 4 of A? Let us just recall. This is equal to, or the only possibilities are 0 and 1. And that's equal 0 if this A is congruent to 1 modulo 4, and it's equal to 1 here if A is congruent to minus 1 modulo 4, right? And that's it. And A2, 2, of course, is not a unit. It's a uniformizer in Q2, right? We are working over in Q2 here, is lambda 8 plus of A. And lambda 8 of A, lambda 8 plus of A, if you have at all worked it out, I think it's going to be plus 1 if this A is congruent to plus minus 1 modulo 8, and it's minus 1 if A is congruent to plus minus 3 modulo 8, right? That's it. That seems to be correct. Yeah. Okay. So I claim that these two, okay, for example, let's compute PPP. Huh? What is the Hilbert symbol? PP at P. So I can write this P as minus 1 times minus P. And then I'll get, expanding it, I'll get minus P times P, minus P comma P, and minus 1 comma P, right? But the first factor here is equal to 1 because that's what I've proved. Minus A, P is equal to 1 for every A in P star. So the first factor sort of disappears and I'm left with this here. So minus 1 P, P. And that's equal to, what is minus 1 P, P? That's equal to lambda P of minus 1 if P is different from T. And that's the definition. No, it's not the definition, but this is what we had proved here, right? I mean, where is it? Here it is. So this when A is equal to minus 1, I'll get minus 1 P. P is equal to lambda P of minus 1, right? That's what I've written here. That minus 1 P at P is lambda P of minus 1. If P is different from 2, and it's lambda 8 plus of minus 1 if P is equal to, that's also part of this thing. I mean, what we had, if P is different from, yeah, here it is. That is a special case of this. A is equal to minus 1. This is what it is. Okay, so now we have got formulae for ABP. When A and B are in ZP star, we know what ABP is, APP is, and PPP, of course, we know what it is. This is what I've done here just now, right? So these three values and the basic properties. What properties? Symmetry and multiplicativity of the Hilbert symbol allow you to compute it for any xy in QP. Because every x can be written as some p to the power m times u, and this y can be written as p to the power n v, and then by multiplicativity, etc., you end up with one of these three computations, which we have done. So that's another way of understanding what the Hilbert symbol is. For these three cases, it's very given by relatively simple formulae like this, right? It's complicated for p equal to 2, but for p equal to p odd, it's really simple. I mean, it's just this formula. It's basically, it amounts to the Legendre symbol. So, as I said, there are two ways of understanding this Hilbert symbol. The first is you write down that explicit formula. Okay. Okay. And the second method is to say what it is in these three special cases, and then to say that you get it in all possible cases by multiplicativity and symmetry. That's it. Okay. So here's a theorem that we wanted to prove. The first theorem that we want to prove today, there's another one. And the first one says that if AB are in QP star, and if their sum is equal to 1, then this Hilbert symbol ABP is equal to 1. It cannot be minus 1. So this, I have cooked up a proof which I don't particularly like, because it's a case-by-case analysis. I mean, it works, of course, but it would be interesting to have a more conceptual proof. And if somebody can find it, or somebody comes across a more conceptual proof, I'd like to hear from him. So first we will distinguish P odd and P equal to 2. That's the first dichotomy. Then when P is odd, we will consider the cases the valuation of P is strictly positive, or it's 0 and the valuation of B is also 0, or the valuation of A is strictly negative and it's even, or it's strictly negative and odd. So these are the cases which we will consider for odd P.
I'm here, Professor Delabat.
For P equal to 2, we'll consider even more cases. So if the valuation is strictly greater than 2, or equal to 2, or equal to 1, or both the valuations are equal to 0, or the valuation of A is strictly negative and it's even, or finally the valuation is strictly negative and it's odd.
Professor Delabat, I have a question, if I may.
So,
Professor Delabat, it's Belinda here.
By the way, before I go into this proof, the case-by-case analysis, let me see.
Sir, someone is asking question.
So I don't know whether I can mute other people.
No. Someone is speaking.
Hi, Professor Delabat, it's Belinda here.
That's what some people wanted me. Let me. What has happened? So people.
Hello.
Professor Delabat, can you hear us?
Okay, yeah. I mean, maybe I can. Somehow. I should be able to mute people, but I'm unable to do it. People are. Yeah. Yeah, it seems no.
Hi, Professor Delabat, can you hear me, Belinda, now?
Well, I'm sorry, I'm not able to do it. Mute all. That looks fine, no? Then I have muted myself or what? And let me see.
Professor Delabat?
Okay. So
ma'am, you can chat him
let's
in chat
continue.
box.
Can you still hear me? I'm tuning
Yes.
messages.
Yes, I think we
All
can
the
hear you.
messages.
But are you able to hear us?
Yeah, I cannot hear anybody actually.
Right.
Right. Okay, let me see. Can you hear me now?
Yes.
Yes, sir.
I think I can hear you.
So shall we continue? Is that spurious noise diminished now?
Well, I had another question actually, if I could ask one.
Yes, yes. Berinder, go ahead.
Yeah, thanks. Is there a link between this quadratic Hilbert symbol and the sort of like the Legendre symbol, which just keeps track of squares modulo p?
No, but that's exactly what I explained. Yes, there is. For odd p, you see the Legendre symbol is there only for odd p. And if I go back to the definition here, here it is. Yeah. So now I'm going to use a different pencil, a different colored pencil so that it's visible. So let me use the green here. See, this formula here, Bender.
Yeah.
AB,
So lambda p is the Legendre symbol.
lambda p is the Legendre symbol.
Right, I see. Okay.
A is a p.
Yeah. Okay. Right. That makes sense.
Right.
Right.
Okay.
Yep. Thank you.
Right. So let me continue now. So we had shown that, so that's the explicit definition of the Hilbert symbol. And you can think of it in two different ways. Just use that explicit formula or derive it from these three special cases by multiplicativity and symmetry. Okay. But now I want to prove that it's a Steinberg symbol. You know, that's the catchword here, which means that if A plus B is 1, then this Hilbert symbol ABP is equal to 1. And as I explained, I'll consider all these different cases. Well, there are quite a few cases, but we have to live with it. So let's start. Let's first consider the case when P is odd and VP of A is strictly positive. Now, what does that imply? That implies that B, which is by definition 1 minus A, because A plus B is, we are considering the case A plus B equal to 1, right? So if the valuation of A is strictly positive, then this B is it's a 1 unit. The elements of this are sometimes called 1 units. And by definition, they are the elements of the kernel of pi 1 or the elements of the group 1 plus p zp. 1 plus p zp is a subgroup of zp star. Okay, so B is in U1, and when P is different from 2 and you have an element in U1, it's always a square. So you write B as U squared, then AB is going to be AU squared, which is AU times AU, and the product of, or the square of any element in Z star is 1, so I get 1 here, right? So that was not difficult. You have to consider so many different cases, but most of these cases are easy like this one. Okay, let's consider the case, we still have odd P, and when both the valuations are 0. That was the case when the valuation of A is strictly positive, and the second case was when both the valuations of A and B are equal to 0. A and B are both units. But in this case, we already computed, you know, that ABP is 1. If you don't recall it, I'll just go back a little and show it to you. Here it was. Let me use a different colored pencil. Where is it gone? So no, blue is not good, green. So here, I said if P is different from 2 and A, B are in ZP star, then this Hilbert symbol is equal to 1, right? Okay, so that takes care of this case. That takes care of this case here. Okay. Now let's come to the case when P is still odd, but VP of A is strictly negative. And first, let's consider what happens when VP of A is even. Okay, then I can write A as P to the minus N times a unit. U is a unit, and this N is strictly positive, and it's even. Then I can multiply A and B by P to the N, which is a square, because N is even, right? P to the N is a square because N is even. And I don't change the value of the Hilbert symbol if I multiply any of the arguments by a square, right? A, B, P is equal to AC squared, BD squared, P. Okay, so I now multiply things by P to the N. ABP is A1 minus AP, because A plus B is equal to 1. That's what we are looking at. And we want to prove that in this case, the Hilbert symbol is equal to 1. So we are going to come to this. But A, replace B by 1 minus A, and then multiply both these things by P to the N. So you get P to the N A, comma, P to the N minus P to the N A. But P to the N times A is U, a unit. And here I get P to the N minus U, but which is also a unit. Both of them are units. And in this case, I know that A, B, P is equal to 1 if A, B are in ZP star and P is different from 2. Right? That's the case here. So let's continue. The only remaining case of an odd prime P for an odd prime P is when the valuation of A is strictly negative and it's odd. If it's odd, then N plus 1, I mean, okay, I write A as P to the minus N times U, where N is strictly positive and it's odd, and U is a unit in ZP star, right? So N is odd, so N plus 1 is even, and therefore P to the power N plus 1 is a square, and therefore I can multiply both these things by, multiply both A and B by P to the N plus 1. So I get, okay, I'll get AB is equal to A comma 1 minus A, because B is equal to 1 minus A. And then I multiply by P to the N plus 1. I get PU here, and I get minus P times U minus P to the N here. Okay, so doesn't matter. I expand, right? And I'll get 4 terms. I'll get these 4 terms. Some of them are already known to us. This we know, it's 1 because both these things are units, and this we have computed, or we are not computed. We know that x minus xp is 1 for all x in qp star, right? So that this one is 1, and here I'll get lambda p of u. Here is your relation between the Hilbert symbol and the Legendre symbol, Beringer. So this is lambda p of u, and this is also lambda p of u. Okay, I mean, right, I mean, this, right. So here you get u because this p to the n disappears modulo p, right? And yeah, you get this. The product of these two things is, of course, equal to 1. So the case P odd is done, right? Now we come to the case P equal to 2. And first look at what happens when the valuation of A is strictly greater than 2. So if the valuation is greater than 2, then B, which is 1 minus A, is in U3. And U3, remember, is the kernel of pi 3, or it's 1 plus 8 Z2 as a subgroup of Z2 star. And what we know is that this everything in U3 is a square. It's actually equal to U2 squared. Remember, this squaring map took U2 to U3, or in general, it takes UN to UN plus 1 for every n greater than 2, right? I mean, if P is different from 2, then the pth power map takes UN to UN plus 1 for every n greater than 1. But for P equal to 2, this P equal to 2 and the, wait a moment. Yeah, that it should be okay. Anyway, so we have U3 is U2 squared. So B being in U3, I can write it as U squared for some U in U2. I mean, it doesn't matter where U is, but AB2 is then going to be AU squared 2, and that's always equal to 1. Okay. So this case is easy, you see. Similarly, let's look at this case, P equals 2, but P of A is equal to 2. Here it was strictly greater than 2. So you write your A as 2 squared times U for some unit U, and then AB2 is going to be 2 squared U times, I mean this, that's B, that's 1 minus A. And so you, so what did I do here? Yeah, this can be forgotten. I mean, I just write U here. And then both of them are units. If I forget this, yeah, so both of them are units. And for units, I had this formula, right? If A, B are in Z2 star, then AB2 is equal to minus 1 to the power epsilon 4 of A, epsilon 4 of B. So that's what I've written here. And that's always equal to 1. Oh, because this thing is equal to 1 modulo 4, right? And if epsilon 4 of C is equal to 0, if of course C is congruent to 1 modulo 4. And it's equal to 1 if it's congruent to minus 1, right? So I get this case as well. Similarly, I don't know whether to go through all these cases. Okay. Well, so it gets slightly complicated in some cases. Perhaps this is the last case I will do. Oh, but this is the last case. I mean, there's no, where is it? This is not the last case. So let's consider P equal to 2 and VP of A is equal to 1. So A is going to be twice a unit. U is a unit. And AB2 is A, comma 1 minus A2, which is 2U, comma 1 minus 2U2. And so I expand it, right, but using multiplicativity in the first factor, first argument. And then here I use the formula that x2 is lambda 8 plus of x for every x in U is Z2 star. Right? So that's what I've written here. And here, both of them are units. So I use that other formula for what happens when I have 2 units. So xy2 is for x and y in Z2 star. So this is equal to -1 to the power epsilon 4 of x times epsilon 4 of y. So that's what I've written here. Now, I'm sorry that you have to look at further possibilities. What can u be modulo 8? It can be 1, -3, 3, or -1. And then, what are the values of these things? So, one does this kind of, makes this kind of a table to check that you get this in all possible cases. Yeah, well, I would like something more conceptual, but it's just very computational. And similarly, I'll skip these 2 cases. When P is 2, but the valuation of A is negative, and either it's even or it's odd. And in both these cases, this case is rather short, but here it's somewhat longer, this one. And well, it's not, well, it's just a computation, right? Okay. Right. So let us sort of write a matrix. What you see, when P is odd, this space QP star modulo squares has a basis consisting of these 2 elements, where I choose U to be a unit which is not a square. And when P is 2, Q2 star modulo squares has a basis. Basis in what sense? These are vector spaces over the field F2. So as a vector space, they have a basis. These are bases. The only slight, it's not a difference, but it's somewhat unusual. What is unusual is that even though they are vector spaces, they are written multiplicatively, right? You won't dream of writing Q2 star, which is a multiplicative group, write it as additively. So it's not very difficult to get used to this vector space, which is written multiplicatively. You have to think of it as a F2 space. And then when P is odd, it's of dimension 2. When P is equal to 2, it's of dimension 3. And here's a basis, here is a basis. So I can write the matrix of this symmetric bilinear form. It's a symmetric bilinear, but here it's better to call it symmetric bimultiplicative form. Okay, so I have a symmetric bimultiplicative form on this vector space, and I am asking for, and I have bases of these vector spaces. So I can write down the matrix of this form in this basis. And here's the matrix. If P is odd, where this lambda 4 of P, of course, you'll recall that it just means that it's +1 if P is congruent to 1 modulo 4, and it's -1 if P is congruent to -1 modulo 4. And here is the matrix when P is equal to 2. It's a 3 by 3 matrix because the basis consists of 3 elements. Okay, so I'll finish today by proving this theorem here. The theorem says that whenever I have A and B in QP star, the Hilbert symbol is equal to 1 if and only if this equation has a solution xy in QP. That's what you want to do in mathematics, right? Part of the time, you want to be able to solve equations, or at least tell when they have a solution as a first step. So here is this quadratic equation in two variables, ax squared plus by squared equals 1. It defines what is sometimes called a conic. And we would like to find out if this conic has a point or not. A point is a solution. And the answer to that existence question is that it has a solution if and only if the Hilbert symbol is equal to 1. And that is, and of course, it would not be much help if we didn't know how to compute the Hilbert symbol. But that is what we have done to give an explicit formula and to compute it in various special cases and to show how to compute it in general. So this is a complete answer to this question as to when this conic has a point, or this quadratic equation in two variables has a solution in QP. Okay, so before I prove this theorem, I have one sort of small lemma which doesn't have anything to do with number theory. It has something to do with algebra or something. And here it is. It says, let K be any field of characteristic different from 2 and take two elements which are invertible. Then I can write down two equations. I can write down this sort of quadratic equation, the one which we are interested in, and I can sort of write down a more homogeneous version of this equation. And the lemma says that there's a solution xy to this equation. There's a solution xy to this equation if and only if there's a solution stu to this homogeneous equation. Stu different from 0, 0, 0. Okay. And in one direction, it's absolutely clear. If you have a solution xy to this equation, then you take s to be equal to u, t to be, no, oh no, here it is, s to be equal to x, t to be equal to y, and u to be equal to 1, of course. Then you get the solution to your homogeneous equation. You get a solution to it. But the other direction, suppose you have a solution to your homogeneous equation, stu, then of course you can divide by u if u is non-zero to get a solution x equal to s over u, y equal to t over u of this non-homogeneous equation. But you have to work a little harder if u is equal to 0. And I'll let you do the work. Conceptually, it's clear that this should be true. Why is it conceptually clear? Because you see, this equation, it defines a conic. We are in characteristic different from 2, and A and B are invertible. So this defines what is called a smooth conic. And so the solutions of this conic, STU, satisfying this equation, they are in bijection with this K union a point called infinity. And therefore, there has to be a point with U different from 0. Because how many points can be there with U equal to 0? I mean, there can be at most 4 points, right? Right? And so you can change the signs of S and T arbitrarily, but that's it. And so this will have more points, and therefore you can always find a point with U different from 0, and then apply this construction here to get a pair xy satisfying the non-homogeneous equation. Okay, so this, I assume that you can do it. I mean, the remaining case. So now let's come to the theorem. It says that the Hilbert symbol is equal to 1 if and only if a solution xy exists. Okay, so in one direction, it's completely trivial. If a solution exists, then there are, I mean, it may happen that x is equal to 0, but if x is 0, then this y has to be a square, right? I mean, you are left with this equation, means that y is a square, and therefore ABP is going to be equal to 1, because not y, b has to be a square. If b is a square, then ABP is equal to 1, as we have seen. So in this case, the Hilbert symbol is equal to 1. If y is equal to 0, it's the same. I mean, then A has to be a square, and therefore ABP is going to be equal to 1. If both x and y are non-zero, then what happens? Then ABP, I can multiply A and B by squares. So I multiply it by x squared here and y squared here. So it's going to be ABP is going to be AX squared, comma, BY squared P. But that's equal to 1, because whenever I have C plus D equal to 1, I have CDP equal to 1. Okay. So this implication that if, I mean, I think it was in this direction, if there is a solution, then the Hilbert symbol is trivial. So now we are proving it in this direction, which is to say that we are assuming that the Hilbert symbol is equal to 1, and we want to find a solution xy to this equation. Okay, so before we do it, there's one simplification, which is that if I interchange x and a and b, I don't change the value of ab, right? Because this Hilbert symbol is symmetric. Similarly, I don't change the fact whether this equation has a solution or not, right? Similarly, I can replace a and b, I can multiply a and b by squares without changing either the Hilbert symbol or the existence of solution xy to this equation. So by this symmetry and this sort of multiplication by squares, we are reduced to the following 3 cases for the valuations of a and b. Either the valuations of a and b are both 0, or they are both 1, or one of them is 0 and the other is 1, because the case 1, 0 is taken care of here by interchanging a and b. Okay, so we just need to look at these 3 cases when the valuations, when a and b are both units or both uniformizers, or one of them is a unit and the other is a uniformizer. Remember, a uniformizer is an element of valuation 1. Okay, so in fact, we can reduce this case when both of them are uniformizers to the case when one of them is a unit and the other is a uniformizer by this substitution. You replace A by minus A times B inverse. Well, of course, you have to check that this replacement doesn't change the Hilbert symbol, and it doesn't change the existence of a solution. So let's check it for the Hilbert symbol first. What is minus A B inverse comma B at P? By multiplicativity, it's ABP and minus B inverse BP. Now ABP, keep it as it is. But this one I can multiply by b squared to get minus b instead of minus b inverse. And then minus bb is equal to 1. So I'm left with ABP. So this is equal to this, right? So the Hilbert symbol doesn't change if I replace A by minus A B inverse. Similarly, the existence of a solution xy should not change. That's because of this little lemma which I proved before I started proving the theorem. What did that lemma say? That this inhomogeneous equation will have a solution xy if and only if the corresponding homogeneous equation has a solution different from 0, 0, 0, right? So there exists xy satisfying this equation if and only if there exists stu different from 0, 0, 0, which satisfy this homogeneous equation. Now, this homogeneous equation, here I can multiply throughout by b and then simplify meaning then rewrite as this. So if the first equation has a solution, then this equation also has a solution. Of course, the same solution, basically. But this I can dehomogenize now, and that means that there's a solution xy to the equation ax squared plus by squared equals 1. So this equation has a solution if and only if this equation has a solution. So the upshot of all this is that I can replace A by minus A B inverse, and therefore I can forget about the case when the valuations, when both A and B are, wait a minute, here. When both A and B are units, or uniformizes, this case I can forget about it altogether. Okay. Right. So let's get going. So I have these three cases now, 0, 0, 0, 1. No, I have just two cases. Yeah. So I'm looking at this case 0, 0. A and B are both units. But let me first look at odd primes P. And let's define S to be this subset of Fp. It consists of A times a square. And the square, so how many elements does this have? You should check that, this set xi squared, xi in Fp, how many elements does it have? I believe that, it has p minus 1 over 2 plus 1 elements. This 1 is for 0, and this is for the in Fp star. So this is perhaps equal to p plus 1 by 2. So that's the number of elements in this set. And if I look at the set T, which is 1 minus b bar eta squared, where eta is also in Fp, then it has the same number of elements. So each of them has exactly p plus 1 by 2 elements. Now, what does that mean? I mean, I have this S, T are subsets of Fp. This has p elements. This has p plus 1 by 2 elements. This has p plus 1 by 2 elements. So the sum of elements here is p plus 1. Which means what? It means that S intersection T is not empty. That's what I've written here. So there exist x and y in Zp such that ax squared plus by squared is congruent to 1 modulo p. That's what you see. This is ax squared. This is 1 minus by squared, 1 minus by squared, and the sum is 1 modulo p. Okay. So, I mean, of course, I can rewrite this as as this here. Meaning this thing here, what is this? This is a unit in ZP. This is in ZP star, of course, right? Because A and B are in ZP star. So this is in ZP star, and it's congruent to a square modulo P. Well, if it's non-zero, then, oh, well, it was a unit, or 1 minus B squared. Well, A and B are units, but I'm not claiming that this whole thing, this expression is a unit, huh? But if X is congruent to, if X is not 0 mod P, then it's of course a unit. And not only is it a unit, it's the square of a unit, because it's congruent to a square modulo P. It's congruent to a non-zero square modulo P if X is non-zero. And if this is this expression is equal to T squared, then of course I get this solution T comma Y to my equation AT squared, AX squared or AT squared plus BY squared equals 1. But what happens if X is congruent to 0 mod P? Then of course B is equal to U squared for some unit. Because if X is congruent to 0 mod P squared, then yeah, this B is going to be a square modulo P, and that's it. So it's if it's a square modulo P, it's going to be a square in the units that's here, and no, that's here, and I get this solution 0 comma U inverse to my equation AX squared plus BY squared equals 1. So that was the case when A and B are both units and P is odd. What happens if both of them are units and P is equal to 2? Then I have to, then the computation of the Hilbert symbol is different. It's given to be equal to 1. So that means that this minus 1 to this power is equal to 1. So this power has to be even. And it's even if and only if one of them is 0, right? I mean, these two things are, what are they? They are, just take the values 0, 1. So the product of these two things is 0 if only if one of them is 0. So let's assume that A is the one which is 0, which amounts to saying that A is congruent to 1 modulo 4. Not A equal to 0. Epsilon 4 of A is equal to 0. So that means that A is congruent to 1 modulo 4. Or equivalently, that A is congruent to 1 modulo 8 or equal to 5 modulo 8. If A is congruent to 1 modulo 8, then of course A is a square. This A is a square in Z2. That's one of the things which we have proved using Hensel's lemma. And we have also used it today. We said U3 is equal to U2 squared. U3 is precisely the set of things in Z2 star which are congruent to 1 modulo 8, right? So if A is congruent to 1 modulo 8, then it's a square. It's a square. And then you get the solution. On the other hand, if A is congruent to 5 modulo 8, then it's congruent to 1 minus 4, because this is 5, right? This is 5. 5 is 1 minus 4 modulo 8. Everything is happening modulo 8. And 4 is congruent to 4b, because for every x in Z mod 8 Z star, 4x is congruent, is equal to 4. I mean, 4 times whatever. 4 times 1 is 4. 4 times 3 is, I mean, congruent to 4, etc. Modulo 8, huh? So, if A is congruent to 1 minus 4b, then this 1 minus 4b A inverse is a square. I mean, that's the same as saying that 1 minus 4b A inverse is congruent to 1 modulo 8. And that's why it's going to be a square. And then you get this solution. Okay. Let's come to the next case. VP of A is 0, A is a unit, VP of B is 1, B is a uniformizer, and P is different from 2. Okay, so then it's a, so the hypothesis is that ABP is equal to 1, but ABP in this case is equal to lambda P of A. And lambda P of A is equal to 1 means that A is a square. There's a T in ZP star such that A is T squared. And then you have this solution, A T inverse squared plus B times 0 squared equals 1. So this is your X and this is your Y. Now the same case, but P is equal to 2. Then this is the final case. Yeah, so I'm sure, yeah. So AB2 in this case, now here is something which is sort of exercise. It needs to be worked out. What is the exercise? To check that AB2 equals 1 is equivalent to saying that either A is congruent to 1 modulo 8 or A plus B is congruent to 1 modulo 8. That's what I'm leaving it to you to check. Of course, under the hypothesis that VP of A is a unit and B is a uniformizer in Q2. Now, if you have checked this, then if A is congruent to 1 modulo 8, then it's a square. Or if A and A minus B are congruent to each other modulo 8, then A minus B times A inverse is going to be a square. So in this case, in the first case, you have these solutions. I mean, this solution, A T inverse squared plus B times 0 squared is 1. And the second case, you have this solution. So it's just a matter of checking these things. So since I have a few minutes, let me also tell you something which is, I've told you one global result. I have not proved it because we are not working over Q, but here is an interesting result which is called the product formula. This was the way Hilbert himself proved it. Hilbert's version of quadratic reciprocity. So some of you might have seen this business of quadratic reciprocity. And here is what how Hilbert reformulated it, and it was a very important development to rewrite it in the following fashion. So the product formula says that the product over all V of A, B, or, okay, let me start over again. So where is this? So it says, let A and B be in Q star now, not in QP star. So I have no prime which is fixed. I'm taking two non-zero rational numbers. Then, of course, this Q is, of course, a subfield of QP for every prime P. And it's also a subfield of Q infinity, which is the field of real numbers. So I can now, goodness, why is this happening? So I now have A, B, V in Z star, plus minus, this is plus minus 1. And this V is either a prime P, or V is equal to infinity. For V equal to infinity, I didn't define it. I left it as an exercise for you, right? To define the Hilbert symbol in this case. The requirement is that ax squared plus by squared equals 1 has a real solution if and only if AB infinity is equal to 1. Otherwise, AB infinity should be equal to minus 1. And that uniquely sort of defines AB infinity. And you have to find an explicit formula for yourself, right? Okay, so what is the product formula? The product formula says that if I take the product over all V of ABV, so V runs over primes union this little funny thing called infinity, the product is equal to 1. This is the product formula, and this is equivalent to the law of quadratic reciprocity. Right? So here is a very small corollary of this. See, earlier I had this theorem of Hasse-Minkowski, which I stated, Minkowski. Which said that this equation A, so again here A, B are in Q star, ax squared plus by squared equals 1 has solutions in Q that was equivalent to this having solutions in QV for all V. This was the original Hasse-Minkowski, but if I now add this to the mix, then I can replace this for all V by for all I can replace it by this for all V, but possibly 1. Meaning, I don't need to check it for all V. If I check it for all V, except 1 for which I don't want to check it, it is still fine. It'll have to have a solution in Q. Why is that? That's because the remaining one is automatically determined by the values at the other V's. Okay? So, right. So you see, it's a very interesting thing. So for example, if here is another way of saying it. Here is another way of saying it. So again, A, B are in Q star. Then I'm claiming that if ABP is equal to 1 for all primes P, then AB infinity is equal to 1. You see, all these QPs combined together know something about the real numbers. I mean, they are so very different. The QPs are so different from the real numbers. But when you combine them together, there's some sort of harmony. You get this product formula. And as a consequence, you can determine whether something has a solutions in real numbers by looking at whether it has solutions in QP for every prime P. Okay, so let me stop here. You have 2 minutes to ask questions if you have any. Otherwise, you can always send me emails. Right? Any questions?
So is there a sense in which this product formula allows you to think about primes as in some sense coming in pairs? So like if AB17 was -1, then there'd have to be another prime for which ABP was -1. Is there something like that going on here?
That might depend upon A and B. So it doesn't give you a pairing of primes, right? You could.
Yeah.
Yeah. So instead of singling out the real numbers here, I could have said if ABP is equal to 1 for all primes P and for infinity, then AB2 is equal to 1. I mean, I could have written it this way as well. So here it is. I don't have any space here. Yeah, here is some space. So I could have written it this way as well. If AB infinity is equal to 1 and ABP is equal to 1 for all odd primes. Or actually, let me fix a prime P. I mean, I was doing it for 2. Fix a prime L, let's call it L. No? Fix a prime L. For all, now I have to say not odd, but all primes P different from L. If these two things happen, then this ABP, ABL
Is 1.
ABL is equal to 1. Yeah. So
I can think of the product formula as saying like 50. There's like a density statement, maybe like 50% of the symbols are 1 and 50% of the symbols are -1.
No. They can't be any such thing. No. Meaning, I mean, sometimes you will just. It says that you can't miss just one prime, but you can always miss 2 primes. You can always miss. Yeah, actually, okay. So that's an interesting question. Actually, you cannot miss a finite odd number of primes, but you can always miss a finite even number of primes. And if you give me any finite even set of primes, I mean, I'm including infinity as a prime, then I can always find a conic which doesn't have points exactly at these places and has points everywhere else. So that's a slightly refined version of this sequence of Brouwer groups, the exact sequence of local to global sequence of Brouwer groups.
Yep.
So yeah, it says that you cannot miss the number of primes where you don't have points. That number cannot be odd. The number of primes where a conic fails to have points has to be even. And given any even set of primes, there is a conic, and precisely one conic, in fact, which
that does not.
Sorry?
That does not have points at those places.
Precisely those points, those primes. That's right. Yeah.
Interesting.
Yeah.
Thank you.
Right. Yeah. You're welcome. Okay, so we'll meet on Monday.
Sir, I
Yes.
had a doubt.
Yes.
So, how are you like defining this infinite product?
Okay. So sorry, it's a good point. I restarted, but I forgot to state it where was it? The product formula is here. Yeah. So it says, it should be, let me write it in red. So the statement is then ABV, I'm using this, is equal to 1 for almost all V and this product form. So now this product makes sense because almost all terms are equal to 1. Yeah, good question. What's your name?
Anupam.
And you are from ISL Pune?
No, I'm from CMI.
Okay, good. Yeah. So the product makes sense because all these Hilbert symbols, if you fix A and B, then okay, you should be immediately able to tell me why ABV should be equal to 1 for almost all B. If you fix A and B, the reason is that almost all V's are actually odd primes at which these A and B are going to be units. And whenever I have A, B in ZP star, P is odd, then ABP is equal to 1. Yeah. So that's the reason. Other questions?
Okay, sir. Thanks.
Yeah. Right. Good. So we'll meet on Monday.